Let's try that again. Good gosh almighty. All right. Sorry for losing my way with you, everybody. I got crashed out of my Wi-Fi. So I'll tell everybody I'm back. First part of the video is gone. Sorry about that. We're answering questions today. All right. I'll wait till you come back. Aaron, I can see it again. Thank goodness. Hallelujah. Okay, Aaron, since you're the first one back, and Noah, can you guys punch this out? So 6.3 times 10 negative second times this ratio, 8.5 over 1,000 and 8.5 times 1.2 times 10 negative third times this ratio, 1,000 over 1,000, 8.5. If you guys could punch that out, let me know what you get. Hello, Rhea. Hello, Quinn. So let's all multiply this out, and then let's see what the tip is, and then we can quickly finish the problem. All right? Sorry that crashed. What can I do? Frickin' technology. Really. It's supposed to save so much time in our lives. Thank you, Noah. I'll write it down. Maybe a couple others can check it with me. 6.4 times 10 negative 7. So let's compare that now. Is it bigger or smaller than up here? Well, there's the KSP. So the tip, if that is correct, is bigger than the KSP. So the answer is what? All right. Okay, Ray's got something different. All right, let's find out. So I don't know what it'll be, Ray. Let me just do it in my head a little bit. That'll be negative third. Negative third times negative third or fourth. Nah, that sounds about right. Somebody else, can you check and see? I think that's about right, Ray. Repunch it in, Ray, and see if you don't get the same thing. That looks about right to me. Because I got negative, I don't know, fourth times negative third should be about negative 7. Anyway, Aaron has it. So there's a KSP. There's a precipitate. Oh, did I look up the wrong value? Now that could be. Although it doesn't really matter, Rhea, because it's still a lot bigger. In other words, the tip is bigger than the KSP, so there's so much stuff floating around, there'll be a precipitate. So the answer is yes. Precipitate. And life is so good. It's so exciting. First thing in the morning. God, I love it. So, yes, there'll be a precipitate. Good. All right. So, but thanks for checking that, Rhea. Catch all my mistakes. Appreciate that. If that's the right, different than right, negative 13 up there. Good. Let's go back because we had another question and I lost it. So you'll have to type it in again, Shilpa. Your other question was lost because I had to delete the other video forever to like get onto a new live stream. So Shilpa or anyone else who has a question on either chapter 4 or ideally 5 and 6, the acid base chapters, just type it in and let's take more of your questions now that we got most of you back. I'll erase this while you're thinking. And hopefully we won't crash again because I can put this in the class chat, or the class stream in Google so you can have it to refer to. I love those will there be a precipitate problems. My gosh. Let's see if I got anything else from our folks at home real quick. Question wise, Noah or Tom. Okay, Tom's back on too. That's good. Well, while you're thinking, let's do a quick review, or while you're typing, let's do a quick review. In a strong titration, at the equivalence point, I'm doing a little review with you in case you haven't figured that out. In a strong titration point, at the equivalence point, pH equals 7. Before or after that, you must subtract the moles acid minus base, or base minus acid, divide by the volume, so divide by total volume, and then get the pH or pOH. So that's the scoop, okay? That's a strong. It's relatively simple. So at the equivalence point, pH is 7. If not, you got to subtract and see who's left over. Is there more strong acid left over, or more strong base left over? Divide by the total volume, and then get the pH or pOH. All right. But if it's in a strong, weak, or weak strong, halfway, and this is the magic spot you have to memorize, halfway to the equivalence point, right, where I'd have the same number of moles of acid and base, halfway to the equivalence point, underline it because it's important, you have a 1-to-1 buffer. And like we said a couple problems ago, the pH at that point equals the pKa of the acid. All right, what about at the equivalence point? This is a review. It's pretty blurry. All right, I'll try one more time. I'll read the whole thing in a sec. Let me finish my train of thought, and then we'll try and do it. Okay, in a strong, well, I take it back. Let's just start from the top, Noah. Okay, so the top says, in a strong titration, strong acid and strong base, at the equivalence point, the pH is 7. Then before or after that equivalence point, you must subtract the moles of acid minus base, or base minus acid, depending which is bigger, divide by the total volume to get the concentration, and then get the pH or pOH. If it's a strong acid, weak base, or weak acid, strong base, then it's another game entirely. The magic point, or a magic point, is halfway to the equivalence point. You have a 1-to-1 buffer, and the pH simply equals the pKa of the acid. Now, it's the acid that is the conjugate of the weak base. In other words, if I do a strong acid, weak base, then the Ka is the Ka of the conjugate acid of the weak base, if that makes sense. It's not the strong acid, because the K is infinite for that. And we did that in a problem just a few minutes ago. We got the Ka of NH4 plus, not HCl. And if it's a weak acid, strong base, then I get the Ka of the weak acid. That's a lot more straightforward. Okay, so sometimes you gotta get the Ka, figure out what your weak acid is, but at any rate, you got a buffer, and this is a really nice thing right there. Halfway to the equivalence point, the pH equals the pKa. So at the equivalence point, if it's strong acid, weak base, the pH, again, this is at the equivalence point, the pH is less than 7. Why? Because the acid's stronger. Kind of makes sense. And if weak acid, strong base, you can just about guess, then the pH would be greater than 7, right? Why? Because the base is stronger, and that's at the equivalence point, EQ point for short. That's the guts of titration right there, this board. That's the guts of titration. So I hope reading it off enough like that, Noah, was helpful for you getting it. I'm sorry it's grainy. I got you about as close as I can without the boxes falling over. I guess my Wi-Fi is a little weak today. Okay, I'm still rolling, so you're still there. Other questions from you? If you got any, please type them in now. I'll look one more time at my phone, see if Tom or Noah D have any questions. It sounds like some of you are still finishing chapter 4. Good, no. Please roll on 5 and 6. I don't even know how to say this. You got a clausura next Monday, okay? And it covers the whole book. So you need to do a little triage. Do what you need to do first. Especially 5 and 6 really need to be done. You can more or less walk through chapter 7 in about 45 minutes, even as a student, and figure out the important stuff. And for chapter 8, there's about one more important thing we'll talk about tomorrow. And then we've covered most of chapter 8. Even though it's long, there's not as much in there we really need. And if you run out of questions, we're going to do more on chapter 8 right now. So we'll see. But I'd rather get all your questions answered. So yes, I know your loads are huge. Try and do as much as you can. It's going to be a stressful week. I know that fully. I can help you only as much as I can. So ask me questions. But looks like we've run out. So if that's the case, then we're going to go back. And I hope all of you watched the video I made yesterday in my little office here where the Wi-Fi was working better. Let's review something from the video yesterday, and then we're going to go on to sections 8.4. That's probably as far as we'll get today, okay? All right, that's fine. So, from yesterday, you'll have to watch the rest of this video later. From yesterday, we talked about reduction oxidation. So we're talking chapter 8. Reduction oxidation, commonly known as redox. Let's just do one to like review for grins, all right? So here's one. IO3 minus plus HSO3, probably minus, yeah, forms SO4 2 minus plus I2. And this is a hard one. And the question I'm going to ask you is, find the pairs. Who's reducing? Who's oxidizing? Who is reducing? Who is oxidizing? Well, the only way we can answer that is with the oxidation numbers. You ready? And we got to take the numbers of the things that are doing something. So we're going to do some of this in our head. Now, for I2, it's easy. It's an element, so the oxidation number is 0. I'll put a little 0 there. How do I know that? All elements, their oxidation is 0. What about over here? Well, this is trickier. It's minus, but I got 3 O's. Remember we said the O's are worth 2 minus a piece? So if the O's are worth 2 minus a piece, then I got 6 minuses, but I got 1 left over here, so the I must be plus 5. All right, so we can tell already the I is the thing that's changing. It's going from plus 5 to 0. Is it oxidizing or reducing? Hint, hint, hint. Look at the number. It's going down, isn't it? So this is reduction. Well, the other one then better be oxidation. Let's make sure of that. This time, what do we got? We got HSO3, and again, we got 3 O's, which is -6 worth. Remember we said the O's are worth 2 minus. -6, but we got a plus 1 because there's an H there, so that brings them down to -5. And I got -1 left, so this must be plus 4. What I'm doing is I'm quickly figuring out what's called the oxidation number of each principal element. Principal element means the things that are not O and not H, okay? Because they're the ones that are oxidizing or reducing. All right, SO4 2 minus. I got 4 O's, so that's -8. I got -2 left here, so this must be +6 to cancel some of that out. And by golly, check it out. We're going, the S is going from +4 to +6. It is indeed oxidizing. And I also did with you there a quick review of oxidation numbers. And that's how I want you to do it, in your head and quickly, because the numbers are not so big. You can do it in your heads. I hope that was helpful. That's a review from last time. And if you want the rest of that problem, it was on page 492. Cheryl does some other things with that reaction, but she balances it all. But we're not going to fuss with that because there's not much of that on the AP. Instead, I'd like you to turn, if you have your book with you, to page 507. Page 507. And again, it's a rule we had that I gave you in the video yesterday. What they do on the AP is they give you everything as a reduction. So we got reduction, half reactions. Half reactions. They call it standard reduction potentials or something like that. It doesn't matter. Here they all are. Goes to goes to goes to goes to. Okay. Why am I doing that? Because I want to review the quickie law. I don't do this because I like students to think, but I want you also to be able to do this quickly. If a redox reaction will go on its own and be what's called spontaneous, right, have a negative delta G, then you need to have the reactant, the thing reducing, somewhere above on the chart and the product, the thing that it's forming, somewhere below. If you have the left one higher and the right one lower, it'll be spontaneous. We're going to do one right now to show you that, okay? And we're going to do two things at once. Yeah. All right. If you got a question, and I know some you need to head off here, so you'll have to watch the rest on video later. If you got a question, type it in. Okay. Let's begin with gold. So look on page 507, please. So find AU3 plus, okay? And then find AG. There's a dream reaction, right? Silver, gold and silver. Ah, gold ion and silver metal. So how do I know it will react? Because if you find the AU3 plus, it's on the left side and it's pretty high up here. And if I find the AG plus, it's on the right side and it's pretty low. So that will be spontaneous. You'll see why I'm telling you all this in a moment. And the delta G will be negative, okay? Like we learned in another chapter, chapter 7. Minus a negative Gibbs free energy, delta G means it's spontaneous. It happens on its own, and the electrons will flow on their own. So what do we get? Well, look on the chart and see, oh, we just get regular gold. And then we get, you know, the silver ion is Ag plus. That one you have memorized. But we got to balance that puppy. This guy loses 1 electron. This guy gains 3, so that's not going to work out. So essentially, we need to have how many silvers, right? We need to have 3 of these puppies, don't we? 3 of these that are losing 3 electrons. And now we balance this thing, okay? All right, let's do something new for this reaction. Let's get the voltage. You might add voltage in physics. Voltage is a measure of the drop in energy of the electrons. I'm sure we'll define it differently, but that's how I think. A measure of the drop in energy of electrons. So they start out as a high potential energy and they go to a low potential energy if it's spontaneous. Okay? Well, we need some data. So we're going to look up on not page 507 because there's no voltages, but in the back of your book. And we're going to look at page 569. That's where I got the voltages, okay? So find the one for AU3 plus. It's towards the top of the chart, all right? And it's a voltage of 1.5 volts. Here, I'm going to write that down again. AU3 plus, when it gains 3 electrons, forms AU. And the voltage, called E0, the electrochemical potential in fancy words, the voltage is 1.50. And it's positive. I can put a plus there to make you feel good. And then the other one is, you'll see why I'm writing this out again. The other one is the silver one, which you're going to find quicker than I because I'm sitting here in a basement. And it's 0.80 volts. Everybody find that? 0.80 volts. But here's the problem. I've got silver metal. So you know what I got to do? I got to flip this equation around. So let's do it. Ready? Silver metal goes to silver ion plus an electron. But guess what that does when I flip it around? What does it do to the voltage? You guessed it, Chester. Instead of being plus 80, now it's minus 80. Minus 80 volts. And you might say, but wait a minute, Mr. Weiss, we still got to multiply it by 3. You're right. You ready? Oh, 3 electrons, so I need 3 here. So I'm going to multiply this whole thing by 3. And the voltage, we do not multiply by 3. Ooh, okay? Yeah, it says E0, Aaron, that's right. And what this is, it's the voltage. You'll see Cheryl also calls it electrochemical potential. It's like the drop in potential energy of the electrons. Anyway, E0 is what that is. That's right. Okay, now, gang, this is super important. If I multiply the equation by something to make the electrons drop out, which I got to do, I do not multiply the voltage by anything. That seems weird. Here's why. This is the amount of drop-in energy of each electron. It doesn't depend on the amount of electrons. Think of it as the height of a waterfall. Even if I have more waterfall coming over the waterfall, the height of the waterfall doesn't change. This is like the height, okay? So that does not change. But to get the overall reaction, we want to add those two together. Okay, 1.5 minus 0.8 is 0.70 volts. So that's our E0 for the cell. I'll use what Aaron asked about. And let's do the balance reaction again. So it's 3Ag plus Ag3 plus forms 3Ag plus Au. So there's our redox reaction. It's balanced. And there's the voltage for the reaction. So it is spontaneous. So the deal is, we said something spontaneous in chapter 7 if the delta G is negative. And it's spontaneous, chapter 8, if the voltage is positive. So over on the side of your paper, let's write that. Ready? Ahua. It means like octone, but in Mr. Weiss language. Okay? Ahua. If the voltage is greater than 0, reaction is spontaneous. And delta G is negative. And tell you where we're going with this. The equilibrium constant, big K, is also greater than 1. Are all those connected? You betcha. Is it hard? No. You just have to think about it. Okay? Think about all the concepts we've had. And this is the last big thing that we round up in the book. Okay? So for electrochemical reactions or redox reactions, if they're a positive voltage, they're spontaneous if the voltage is greater than 0. And it's the same thing if the delta G value, the Gibbs free energy, is negative. And it's the same thing if the equilibrium constant is greater than 1. Remember, we make more products? So I hope that all makes sense to you. It's all related. and it will be all relatable in chapter 8 with equations. Okay, so let me pause here and see if you got any questions. Yes, I know some you need to pull out. Let me see if Noah or Tom got any questions real quick while you're thinking. Okay. All right. So you know what? I'm going to do the rest of this with you. I hope in school tomorrow. I hope. If not, then I'll make a video for you and send it off to you today. Okay? So for the last ones remaining, you're